Hi students, in today's class we are going to discuss the later half of our essay on the liquid drop model. In the previous class we had discussed how we resort to the use of models to explain the structure, properties and the forces acting inside the nucleus. And the first model that we discussed was the liquid drop model, where we considered the extrinsic similarities between the liquid drop and the nucleus, and we tried to explain the binding energy equation or the semi-empirical formula for binding energy suggested by Weizsäcker. Uh, the terms in that equation, the five terms in that equation were explained. In the last session, we discussed about the first three terms, that is the volume energy term, the surface energy term, and the column energy term, based on this liquid drop model. Now we are going to discuss the fourth term, that is the asymmetry energy term. Initially, the equation had only the first three terms, but using these first three terms, when the binding energy per nucleon versus mass number curve was plotted, that is the curve that we learned in our session on nuclear stability, binding energies and mass effect, when that curve was plotted, it did not match with the actual curve. So it was suggested that there must be some correction to this formula. And on its basis, two new additional terms were included into the equation for the binding energy. അതായത് ആദ്യം ബൈൻഡിങ് എനർജി ഇക്വേഷൻ ലിക്വിഡ് ഡ്രോപ്പ് മോഡൽ പ്രകാരം സജസ്റ്റ് ചെയ്യപ്പെട്ട സെമി എംപിരിക്കൽ ഇക്വേഷൻ ഫോർ ബൈൻഡിങ് എനർജി, ആ ഇക്വേഷനിൽ മൂന്ന് ടേംസേ ഉണ്ടായിരുന്നുള്ളൂ. ഒന്ന് സർഫസ് എനർജി ടേം, ഒന്ന് വോള്യൂം എനർജി ടേം, മൂന്നാമത്തെ കുളം എനർജി ടേം. പക്ഷേ ഈ ടേംസ് ഉപയോഗിച്ച് നമ്മുടെ ബൈൻഡിങ് എനർജി പെർ ന്യൂക്ലിയോൺ വേഴ്സസ് മാസ് നമ്പർ കർവ് വരച്ചപ്പോൾ അത് യഥാർത്ഥ കർവുമായി മാച്ച് ചെയ്തില്ല. അപ്പോൾ ഇതിലേക്ക് ചില അഡീഷൻസ് കൂടി അല്ലെങ്കിൽ കറക്ഷൻസ് കൂടി വേണമെന്ന് എന്ന ചിന്ത വന്നു. അങ്ങനെയാണ് ഈ ഇക്വേഷനിൽ ഈ കറക്ഷൻസ് കൊണ്ടുവന്നത്. സോ ദ കറക്ഷൻ ടു ദി ഫോർമുല വർ ദി അഡീഷൻ ഓഫ് ടു ടേംസ്. വൺ ഈസ് ദി asymmetry energy term and the binding and the pairing energy term. So let us go into what is the asymmetry energy term. This term arises due to the lack of the symmetry between the number of neutrons and protons. So if the number of neutrons is not equal to the number of protons in the nucleus, then asymmetry energy arises, and we have to include the asymmetry energy term in the equation for the binding energy. Now let us see what is this asymmetry energy and how does it affect the binding energy of a nucleus. Now, if the proton and neutron energy level spacing is epsilon, then epsilon is proportional to 1 by A. That is, the nuclear energy level spacing is inversely proportional to the mass number or the atomic mass. As the number of nucleons in the nucleus increases, the nuclear energy level spacing decreases. Initially, let us consider n equal to Z. Then, to produce a neutron excess without changing A, what you have to do is the excess of neutrons that you have to bring about, that is n minus Z, the half of it is found out, and half of those many neutrons replace the same number of protons. Now the new neutrons will occupy higher energy levels, and we calculate the asymmetry energy based on this. Now let us consider this the calculation of an asymmetry energy on the basis of an example. Now suppose we have a nucleus with us having mass number 16. That is, the total number of protons and neutrons in the nucleus is 16. Now imagine that This nucleus has 4 protons and 12 neutrons. Then there is an asymmetry in the number of protons and neutrons. There is no asymmetry means there must be 8 protons and 8 neutrons. Because I just imagine that in this case there are 4 protons and 12 neutrons. That means there is an inequality or an asymmetry. Now, to create this asymmetry, some amount of energy has to be given to the system, or some amount of work has to be done on the nucleus, and this is called the asymmetry energy. That is the amount of energy that has to be spent to create the asymmetry, and this energy decreases the binding energy of the nucleus. Now, how to calculate the asymmetry energy? Initially, we draw the symmetric condition, that is when the number of protons is equal to the number of neutrons. In a nucleus of 16 nucleons, under the symmetric conditions, number of neutrons equal to number of protons is equal to 8. So, there are 8 protons drawn here, 8 neutrons represented here. Now, if the neutron and proton energy level spacing is epsilon, then I have already told you epsilon is proportional to 1 by A. Okay, as the number of protons and neutrons in the nucleus increases, that is, as mass number increases, the the nuclear energy level spacing, that is, the neutron and proton energy levels decreases. Now, if the actual nucleus has Z equal to 4 and N equal to 12, that is, number of protons equal to 4 and number of neutrons equal to 12, then we calculate how much is the excess number of neutrons. Here the excess number of neutrons is 8. There are 8 neutrons more than the protons. Now what should we do to create these 8 excess neutrons? What we do is we find the half of it. That is half of n minus z. That is half of 8 equal to 4. This means that you have to replace 4 protons with 4 neutrons to create an excess of 8 neutrons. Is this true? Let us see a representation here. Now initially both we took it as equal, that is 8 protons and 8 neutrons. Now what we do is we replace half of n minus z. What is half of n minus z? In this case it is 4. So we replace 4 protons with 4 neutrons. That is, the 4 protons here is removed, and instead of that we add 4 neutrons. So 4 protons have been removed and 4 neutrons have been added. So what has happened, you see? Now there are 4 protons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 neutrons. This is our necessary condition. This was what I imagined, that my nucleus should have 4 protons and 12 neutrons. Now what has happened to the energy here? Here, the new neutrons will occupy, so these are the new neutrons, these two and these two. The new neutrons will occupy energy levels higher in energy by 2 epsilon than those of the protons that they replaced. That is, these 2 protons were replaced by these 2 neutrons. Now what is the energy difference between them? The energy difference between them is this much is epsilon and this much is again epsilon, so that the energy difference between them is 2 epsilon. Again, these 2 protons were replaced by these 2 neutrons. Again, the energy difference between them is given by 2 epsilon. So the new neutrons occupy energy levels higher in energy by 2 epsilon than that of the neutrons, than that of the, it's not neutrons here, than that of the protons they replace. So 2 epsilon is equal to, I replace 2 epsilon as 4 epsilon by 2. So what is 4? 4 is half of n minus z. That is half of the excess neutrons. So half of n minus z into epsilon by 2 is my excess energy. Now, therefore, what is the total excess work that needs to be done to create the asymmetry? Total excess work is it is the asymmetry energy into the total new number of new neutrons. So the excess work needed to be created is delta E is equal to the number of new neutrons that we have added and the energy increase per neutron. So the energy increase per neutron is given by half of n minus z into epsilon by 2, and the number of neutrons is again given by half of n minus z, so that the total excess in energy is given by half of n minus z into half of n minus z epsilon by 2 into epsilon by 2, that is 1 by 4 into n minus z the whole square into epsilon by 2. 1 by 4 into what is n minus z? N is the number of neutrons. Number of neutrons is equal to mass number minus number of protons, that is A minus Z. So A minus Z the whole square, that is A minus 2Z the whole square into epsilon by 2. We know epsilon is proportional to 1 by A. So I can replace this epsilon with 1 by A when I replace all the constants here with A4. So A is equal to, I replace the constants, that is 1 by 4, 2 and all are replaced by A4. So I can also replace epsilon with its proportional constant, that is a proportional value, that is 1 by A. So EA is equal to A4, all the constants taken together, leaving just the terms in capital A. So A minus 2Z the whole square by A. It is given a negative sign because such asymmetries add to a decrease in the binding energy of the nucleus, or it reduces the binding energy of the nucleus. So a negative sign is given here. I hope symmetry energy calculation and how it affects the binding energy of the nucleus is clear to all of you. We know that a nucleus is most stable when the number of neutrons equal to number of protons. Once the asymmetry is created, stability goes on decreasing. Next, we come to the pairing energy term, that is the fifth term in the semi-empirical formula for the binding energy. So this pairing energy arises from the tendency of protons and neutrons pairs to occur. We have already learned earlier that even nuclei are the most stable. So if our nuclei contains even number of protons and even number of neutrons, then A5, that is the constant in the in our fifth term, is positive. If we have odd nuclei, that is odd number of protons and odd number of neutrons, then A5 is negative. And our constant A5 is 0 when the nuclide is even odd or odd even nuclei. And this term varies as A raised to minus 3 by 4. So pairing energy EP is equal to plus minus or 0 A5 A raised to minus 3 by 4. So pairing energy varies according to A raised to minus 3 by 4, but it will be positive, negative or 0 depending on whether your nuclei is even, odd or even odd or odd even. Okay. So this term will be positive if it is even, negative if it is odd, and it will be 0. So the term cancels off if it is even odd or odd even nuclei. Now based on all these 5 terms, graphs were plotted, that is binding energy per nucleon versus mass number. Graph was plotted. So volume energy is directly proportional to A, so that it is represented by a straight line. Now the surface energy term ES is proportional to A raised to 2 by 3. So it will be like this. The graph is plotted in this manner. Coulomb energy term is given by, it has a dependence A raised to 1 by A raised to 1 by 3, that is it's inversely proportional to 1 A raised to 1 by 3, so it will show a variation like this. And incorporating our symmetry and pairing energy term, the total energy or the total binding energy per nucleon versus mass number shows this pattern that we have already seen earlier. So I hope the liquid drop model is clear to all of you. This is a very important essay as far as our exam is concerned. So kindly go through it very seriously. If you have any doubt, please do contact. Thank you.